Hi, I'm Michael Osman of Great Scott Gadgets, and this is Software Defined Radio with HackRF, Lesson 8, On-Off Keying. In this lesson we will receive and analyze a radio signal from one of the simplest types of digital radio transmitters, a garage door opener remote. The first thing we'll need to know in order to receive the signal from this device is its frequency of operation. There are technical means of determining the frequency, but my favorite method is to use the FCC ID that is printed on the device. Let's see what public information the FCC makes available about this equipment. If you direct your web browser to fcc.gov, you'll go to the website of the Federal Communications Commission, or FCC. The FCC is a government agency that manages radio spectrum in the United States. Now, of course, there are agencies that manage spectrum in other countries, but the FCC is unique in the tremendous amount of information that it makes available to the public about equipment authorized to use radio spectrum. We're going to look under Tools and Data, Data. And if the FCC website changes, you'll probably be able to find this by looking for the word Data. And then under Data, search FCC databases. There is a long list of databases available for us to search, and we are going to look at the Equipment Authorization Search. We're interested in equipment, this garage door opener remote, that is authorized to transmit radio signals within the United States. And here we find, under Equipment Authorization Search, that we can search for a variety of fields. We're only going to use the first two fields, the grantee code and the product code, which are portions of the FCC ID that is printed on the device. A grantee is the organization that has granted this authorization, and then the product code is the particular device, and that code is issued by the grantee. In the case of the garage door opener remote that I have, the complete FCC ID is HBW2392, and the first three characters there I should cut and paste into the grantee code, because the first three characters are the grantee code and the remaining characters are the product code. Now, in the past, all grantee codes were 3 characters long, but the FCC has recently begun issuing 5-character grantee codes. So for newer equipment, you may find that the FCC ID consists of a 5-character grantee code and then some number of characters of a product code. But most equipment, you'll find, has a 3-character grantee code, and then the rest of the code is the product code. But it isn't always clear exactly where the delineation is. So watch out for that. You might misinterpret a 3-character code as being a 5-character code, or vice versa. Once we have the grantee code and the product code entered into this form, we can start our search and see the listing of the authorizations for this device. And this device is kind of interesting because all on the same date in 2007, this device was granted authorizations to operate at a number of different frequencies between 300 megahertz and 390 megahertz. I'm going to look at the detailed listing for one of these, and this should bring up a list of documents in PDF format that I can look at. And one of the first things I like to look at is the external photographs. The reason I like to look at external photographs is because it helps me verify that this is in fact the device that I have in my hand. And yes, this looks like the device that I have in my hand. And you can almost see the FCC ID printed there. If you really want to see where that's located, you can see the ID label and location. And this should be a diagram that shows us exactly where on the device the FCC ID is printed, HBW2392. And in this case, it's actually embossed, or it's part of the plastic mold, as opposed to being printed on after the fact, which means that if this device were sold in another country, it probably would still have the FCC ID on it because it's part of the plastic mold. And that's very common. Even if you live in another country, a lot of the radio equipment that you might find in your country may still have FCC IDs printed on it, even though it wasn't sold in the US, just because it's a product that could be sold in the US. And the next thing I like to look at is the internal photographs. The internal photographs are fun because it gives you a look under the hood. It lets you open up a device virtually and look at it in your web browser without having to actually open the device yourself in person. And that's especially handy if you're trying to get information about a piece of equipment that you don't even have in your possession. In this case, this is an unusually complicated circuit for a garage door opener remote. It isn't tremendously complicated. It isn't anywhere near as complicated as, say, a hack RF, but it is more complicated than a typical garage door opener remote. And the reason that it's more complicated is because it's a universal remote. It has the ability to emulate many different types of garage door opener remotes. So we have a couple of different chips, and this looks like a crystal and a coin cell battery and a series of dip switches. It looks like 12 switches, a couple of buttons, and then another button down here. And these two buttons are exposed to the outside, which you can see if you look at the external photos. This button is not exposed to the outside unless you open the battery compartment, which you can see right here. That third button is exposed, and these dip switches are exposed when you open up the battery compartment. And those other two red buttons are pressed with these two buttons here. So it's a two-button universal garage door opener remote. And if you know a little bit about electronics, this can be a very useful tool for reverse engineering how the circuit works. Sometimes you can even read the identifiers that are printed on chips in the device, or read the crystal frequency and so forth. But in this case, it's pretty hard to make out some of those features. But you can easily see that it is more complicated than a typical garage door opener remote that only supports one type of radio transmission, which you will see if you open up one of your own devices, perhaps. Now I'd like to take a look at the user manual, and presumably this is the same information that is provided to the user and actually ships with the device. And this is often very handy, especially if you don't have the user manual yourself. This is a great way to be able to find the user manual for a device that if you've lost a manual or you're borrowing a device for somebody. And notice here that most of what this one-page manual tells us is about how to program it for the various different modes of operation under Chart A and Chart B. How many numbers of times you have to press the button during its setup in order to get it to go into that particular mode where it's emulating a certain device. And the the big important document that I really get a lot of information from in a typical FCC equipment authorization filing is the test report. The test report contains the information usually from an independent test lab that measures the emissions from the device to determine if it is compliant with particular FCC regulations. Now, there may be other interesting documents here. I'm not going to go through every single one, but when you look up a particular device, you may find some other things like a block diagram or a theory of operation. There could be all kinds of different documents that were submitted with this filing and are made available to the public. In this case, I think we're going to get a lot of information from the FCC test report. And this says, yes, it's a universal 2-button remote control transmitter. And it's quite a long report. This is 83 pages. And one of the reasons it's so long is because they tested this device in all of its different modes, in the modes where it's emulating one type of remote or emulating another type of remote. And if we scroll down, we're going to see some information here, like the particular frequencies that it's intended to operate at and its operating mode. Now this is interesting because these correspond to those modes that were listed in the user manual, but in this case it tells us a little bit more. Like here, this first one is a 10 position dip switch, and then the second one is a key lock based secure code, and then here's a dip switch and a dip switch, and then here's a new rolling code. So some of these modes apparently use a rolling code, that is to say that the code that is transmitted changes. Every time you push the button, a new code is generated, as opposed to these other modes, let's say dip switch, which are presumably fixed codes. That is, every time you push the button, the same code is transmitted over and over and over again. And it'll be interesting to see which format this particular device is using when I push one of its buttons. If we scroll down a little bit further, we'll see some information about the results of the test. And for the most part, this information isn't going to be too interesting to most of you yet. However, as you learn more about radio communications, you may find more and more that you understand what more of this means, and that it could be useful information. You can see a little diagram of where how they set up the test, and photos from the test. And then we get to these actual test results that are the screenshots from test equipment. And you can see these bursts that are of transmission over time in this particular mode. And then here, maybe zoomed in, or a different configuration. And I'll keep scrolling down, and you can see that the transmission looks a little bit different depending on what mode it's in. In this mode, there's a little bit of a gap here that's kind of interesting between a long series of pulses. Here's a mode where you can see pulses of different length, which is quite interesting. And so now that we know a little bit about this device, and we know that it can be set up in a variety of different operating modes, we also know that it can operate on a variety of frequencies between 300 megahertz and 390 megahertz. Now we know enough information that we can go poking around with HackRF and GNU radio and see if we can locate the signal directly. And once we do, maybe we'll be able to compare the results, compare the signal that we receive to some of the diagrams in this document. Another FCC database that is very useful when looking for equipment authorizations is the grantee search. The grantee search allows us to look for grantees instead of looking for individual pieces of equipment or individual authorizations. So if we type in a grantee code, for example HBW, which was the grantee code we saw before, we see this grantee name and a little bit of information. Not a whole lot. But what's more interesting is if we go back and instead of filling in a grantee code, we fill in a name, then we should find that we can find the grantee code that way. This is extremely useful if you're trying to find information about a product and you don't have it. You don't know what the FCC ID is, but you do know who manufactures it. You can look up that manufacturer and find a grantee code. Unfortunately, this doesn't work every time. Sometimes you'll find that the name of the company that you do know is not listed in the database as a grantee, but there's some company that you don't know that is listed, and the equipment you're looking for is actually under that grantee. This happens sometimes if there's an OEM relationship or there's a partner company that is doing the equipment authorization on behalf of the company that you've heard of, or you've heard a brand name but you don't actually know the name of the company behind it. Those kinds of things happen a lot. And one trick that I've found is that if you're looking for something and you don't find it right away, look up the address of the company that you're looking for, and then see if you can find another company in the grantee database that has the same address or a similar address, a nearby address. For example, here we can see when I search for Chamberlain, we can see 3 different companies that all have the exact same address that have different grantee codes. So we might find different equipment listed under different grantee codes that all belong to the same group of companies that share the same address. And one really nice thing about the grantee search, if we go back to the grantee search page, is that you can download all grantees on file in one big XML file. Do this. Download this file. It's very handy to have a copy, and then you can search through it yourself locally to find information about grantees. And once you know a grantee, once you know a grantee code, then you can go back to the authorization search, the equipment authorization search, and just fill in that grantee code. Leave everything else blank. You don't need the entire FCC ID, and you can get a list of all the equipment authorizations for that particular grantee. This list happens to be pretty long. Here we have 217 records. Remember that the device we were looking for had several different authorizations, so this number 217 really probably isn't 217 devices, it's just 217 authorizations spread out over some smaller number of devices. Now, the FCC website isn't the most user-friendly thing, and sometimes it changes. It's a little bit difficult to find what you're looking for sometimes. So I want to show you another website that is very useful. If you go to fcc.io, this is a little tool that was put together by Dominic Spill, and it is a quick and easy way to search for equipment authorization. You can look for any FCC ID or a grantee code. For example, if we type fcc.io/HBW, you don't even have to go into you don't even have to type it in here. You can just type it in the URL, and it automatically redirects you to the results of the search. And you can type in a complete code like fcc.io/HBW. I'll use one of these as right here up front, 0708. And it'll just take me to the authorizations or authorization for that particular FCC ID. I'm going to use GNU Radio Companion and a HackRF1 to try to receive the radio signal from the garage door opener remote. I'll start with a source, an Osmocom source, to receive data from the HackRF1, and I'll visualize the signal with an WX GUI FFT sync from instrumentation WX. Connect these together, and I need to configure the sample rate. I'll set it to 2 million or 2E6, which is the lowest sample rate that I recommend using with HackRF1. And then of course I like to turn off the RF amplifier. And I need to set the frequency to something between 300 and 390 megahertz. Why don't I use a slider for that? I'll call my variable freak. And now I need to create that variable. It will be a GUI widget WX GUI slider. I'll call it freak. Give it a default value of 300 million or 300 E6, 300 megahertz. And I'll set the minimum to 300 E6 and the maximum to 400 E6. And somewhere in that range we should find the signal from the garage door opener remote. Now I'll run my flow graph, call it lesson8.grc. And this lets me visualize the radio signal at 300 megahertz being received by the HackRF. Now I'll click the button on the remote, and I'm not seeing much. So let's try sliding the frequency up while I click the remote. Oh, there's something. Right at 310, or just below 310. I'm holding down the button of the remote. And sometimes I like to use the peak hold feature. That's helpful to find signals that are fairly transient. Or the average feature. The average allows me to get an idea of the bandwidth of the modulation. And you can see the bandwidth is pretty narrow. It's just about as narrow as this spike in the middle here that's at 0 hertz. Of course, that is my DC offset, and we'll talk more about the DC offset in the future. But there's always a bit of a DC spike, or a 0 hertz spike that we see. And since I'm tuned to 310 megahertz, something just below that 0 is something that is just below 310 megahertz over the air. So it's around 30 or 40 kilohertz below 310 megahertz. Pretty close to 310 megahertz, and it's definitely there while I'm holding down the button. Definitely not there when I release the button. And you can see that happen more abruptly if I turn averaging off. Now, one way to be absolutely sure that this is the device, that the signal we're seeing is in fact the device we're looking for, is to turn on the transmitter and then move it closer to the HackRF. And if I do this, you should see that the spike gets higher. It's up around, oh, look at that, way up there. If I hold it right next to the antenna of the receiver, you can see, and we're actually getting some other frequency components because we're distorting a little bit, because we're way up about pretty close to 0 dB. But if I hold it at a more reasonable distance, like a meter away, then I'm at somewhere around -30, -40 dB, and we seem to get a nice clean signal for as long as I hold down the button. Now, the next thing I'd like to do is to visualize this signal using a scope sync. A scope sync is like an oscilloscope. I'm going to stop this flow graph, and I'll use under instrumentation a WX GUI scope sync. I'm just going to connect that to the same source. So now I have one source going to two syncs. And I might as well set my default frequency now to 310 E6 because we know that that is the frequency we should be expecting this signal on. If I run this, now I'll turn off auto range and just adjust my counts per division a little bit. I hold down this, now you can see, I'll keep going with counts per division, there we go. Now you can see kind of complete periods of these bursts happening. Now sometimes there's very little going on. You can see this these two lines, blue and green, going right around 0. But then at other times we get these flickers of activity, of these big sort of sinusoidal curves that are clearly have an amplitude much greater than 0. And if I increase my number of seconds per division, that allows me to kind of zoom out horizontally or zoom out along the time axis. And we can see that there are these bursts of transmissions that happen. I keep zooming out, and you can kind of see a pattern here. If I stop this, let me try stopping it. I'll just run and stop it until I get a whole set of bursts. And if you look closely, you can kind of see the difference between the burst and this stuff around 0. This is a short burst, and then a short, and then a long, and there's a little bit of 0 there, and then another long. So it's short, short, long, long, short, long, short, 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 long. And one of the things I notice about this is that this pattern, short, short, long, long, short, long, short, 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 long, is the same pattern that I have the dip switches set to in the garage door opener remote. They're set to 0011 01 0001. And actually there are 2 more dip switches, but we seem to be only using the first 10 here. The first 10 dip switches correspond exactly to this pattern of short and long pulses. And another thing you might notice is that the beginning of each pulse seems to be the same amount of time, from the beginning of one pulse to the beginning of the next, and then from the beginning of the second pulse to the beginning of the third, the beginning of the third pulse to the beginning of the fourth. And you'll often see this with digital transmission systems, that the symbols are evenly spaced over time. It isn't always true, but it's usually true. And sometimes you might see the end of a pulse lining up, or in this case we see the beginning of a pulse lining up. And if I release the button and press it again, and if I run this some more and stop it and try to get that whole set of pulses on screen at once, we see the same exact pattern. Short, short, long, long, short, long, short, 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 long. The same pattern of 10 bits over and over and over again in these groups of 10 pulses. This modulation is known as on-off keying. It's the simplest form of amplitude modulation. The amplitude is changing to extremes. The transmission is either on or off, and that's why it's called on-off keying. In many ways, it is similar to Morse code. You can imagine this type of transmission coming from a telegraph key. You could manually hit a telegraph key, short, short, long, short, and so forth. However, you couldn't do it, a human couldn't do it this fast. Notice that we're getting pulses, many pulses over many milliseconds here. We're looking at maybe in the neighborhood of 1 pulse per millisecond, or maybe 2 milliseconds per pulse, somewhere around there. This is much faster than a human could key manually, but it's the same type of transmission. You might call it a CW transmission, which is what folks call Morse code, but in this case, since it's produced digitally by a digital electronic circuit, and it's produced much faster than a human could, I would definitely call this on-off keying. It doesn't look like the frequency changes over time. When we look at the average in the FFT plot, it's very consistent and narrow, very narrow band signal. And if we were to look in the scope sync and look at the, if we zoom back in again on the time axis, you can see that every time we see this sinusoid, it does look quite consistent, right? Every time it looks like it has the same period every time it shows up here. And so those are 2 indications tell us that this frequency, or that this signal, isn't changing frequency over time. It is changing its amplitude to extremes. It's being shut on and off. Now if we look back at the test report, remember we found this signal just around 310 megahertz. If we look back at the test report, we should see that among these various plots, we should find something around 310 megahertz. This one was at 300. This one's at 310. This is configuration 18. And it looks like 1, 2, 3, 4, 5, 6, 7, 8. This is 8 pulses. We should be finding something with 10 pulses. If we keep going down, here's configuration 16 at 309.95 megahertz. That is very close to the frequency that we found. And this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pulses. 10 pulses, groups of 10 pulses. And you can see this is 10 milliseconds per division, so we could go back and line that up exactly, but I think what we have here is the configuration, configuration number 16, and it is in the test report here. It looks like they have all the dip switches set to the same position, the on position, which gives a long pulse. In my device, I have the dip switches set to various positions, and so we get a pattern of short and long pulses. And if we look back at the user manual for this device, sure enough, under 16, configuration 16 is a 10-position code at 310 megahertz. So this user manual agrees with the test report, and they both agree with what we're finding under GNU Radio Companion. Now I'd like to take this just one step further and visualize the demodulated waveform. If you remember from lesson 7, we talked about an algorithm for demodulating an amplitude modulated signal. If you have a complex valued signal, which we have here, we should be able to take the magnitude of each sample and look at the magnitude over time instead of looking at the complex value over time, or the real and imaginary parts independently. So I'm going to go into Type Converters and select Complex to Mag. Could also use Complex to Mag Squared, as I talked about in lesson 7. And I'll just plug this in here between the Osmocom source and the scope sync. But then of course I need to make my types agree. The complex to mag block takes complex input and produces real valued, or a floating point output. So I just need to go into my scope sync and change its data type to float from complex. Now let's run this flow graph again. And this time the scope plot looks a little bit different, but if I hold down the button on the remote, I should be able to adjust my settings here. I'm turning my counts per division up quite a bit, and then I'm going to turn up my seconds per division, and we should start to see a pattern emerging. I'm going to increase my counts per division again. Here we go. Now we're seeing the individual bursts looking like these square peaks. If I stop this, look at this. You can see short, short, long, long, short, long, short, 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 long. And it's a little bit clearer and easier to read now that we're looking at the magnitude of the sample values over time. So we don't, within one of these bursts, we're not seeing a sinusoid. We're seeing the magnitude of that sinusoid. And you can see it's fairly consistent. It's a little bit spiky, a little bit inconsistent, but you can clearly see the difference between when the signal is on and when the signal is off. And it wouldn't matter how much of a frequency offset we have here. We should still see the same sort of pattern emerge after the demodulation step. For homework for this lesson, I would like you to find your own garage door opener remote or other simple digital radio transmitter, perhaps a remote keyless entry system for an automobile, and see what you can find out about it. Go to greatscottgadgets.com/SDR, and under Lesson 8, you'll find a series of questions that I hope you'll be able to answer about your own device. And I hope I'll see you next time for Lesson 9.